going to the exact topic of analysis and design, let's summarize what we had covered yesterday. So this was the basic thing. Mealy and Moore machines, we had discussed that Mealy machine is that machine in which the final output is dependent on this state and this external input. But in case of a Moore machine, the output is dependent only on this thing, only the present state. Okay. So this is a basic difference between Mealy and Moore machine. Then we had covered this difference between Mealy and Moore. So first 2 points we had already covered. The third and fourth point we had left in previous lectures. Now we can cover these points as well because we had covered the state diagrams. So you can check that in Mealy machine, output is dependent on input. Okay. So you can see that in the state diagrams which are designed for Mealy machines, on these transition arcs means when we are moving from one state to another state, then both input slash output is mentioned. That means if I mentioned it 1/0, that means if I get input as 1, then output will be 0 because output is dependent on the input. So that is why we can see that this output is mentioned on this state transition arc. Okay. But in case of a Moore machine, the output is not dependent on, or we can say output is independent of the input. So we can see that these state transition arcs are not having values in terms of this slash that, x slash y. So this is not in Moore machine. We can see that there is only single binary value in Moore machine, x is equal to 0, x is equal to 1. Instead of mentioning the output on this transition arc, we are mentioning the output inside this circle. You can check here that state is 0, output is also 0 because output is only dependent on the state. So that is why output is mentioned with the state inside the circle only. Okay. So this is the basic difference between Mealy and Moore machine. So this point which we have mentioned here, outputs are function of states only, that is why output is mentioned inside the circle, that is inside the state circle only in case of Moore machine. But in case of a Mealy machine, output is dependent on input as well, that is why output is mentioned on the state transition arc. So I hope this point is clear now. We had left this point in yesterday's lecture. Okay. So let us proceed further. Then we had covered this state reduction. In state reduction we were trying to reduce the number of states. So initially we were having 7 states, then we saw that these states, this G and E are identical, so we replaced G with E, then 7 states became 6 states, and in that then we see that F and D are same, so we replaced F with D, and then I saw that final states are 5. So this was the state reduction part. Okay. This we have already covered in our yesterday's lecture. Then we had started this analysis. Now I am restarting this analysis from the very beginning. So we will be provided with the circuit. Analysis means that we need not to prepare the circuit, circuit is provided to us by the examiner, and we have to analyze the circuit to prepare the state diagram. Okay. So this is the state, this is the circuit in which we can see that there are 2 flip flops. This is flip flop A and this is flip flop B. The output are also denoted as A and A complement, B and B complement. This is the final output of the circuit Y. Okay. So in this we can see that these are the steps. First step is the understanding the behavior and type of the given circuit. So understanding the behavior means that it is a sequential circuit which is having common clock, that means it is a clocked sequential circuit, or we can say it is a synchronous sequential circuit. Okay. Then the first step is to write the flip flop input equations. So by flip flop input equations, whatever we are applying at the input of the flip flop, that means dA, this dA is equal to this thing, this is my input X. So this X is appearing here and here, and this thing is A and this thing is B. So ultimately this input becomes AX plus BX. Okay, so that's why it is mentioned here dA is equal to AX plus BX. Okay, similarly this dB is equal to this thing, this point is getting connected here, that means B, this is B, and this point is equivalent to X. Okay, so we can see that dB is equal to, this thing is, sorry, I have connected it at the wrong place. This point is here, A bar, this is not B, this is A bar. Okay, I am erasing it. So this is A complement. Okay, so that means dB is equal to A bar into X, that means dB is equal to A bar X. Okay, so this is the first step, flip-flop input equations. Then flip-flop output equations, because this is a D flip-flop in which we know that the output is exactly similar to the input. That's why the next output of this D flip-flop, which is denoted by, right now we have denoted the outputs as A and B. So the next state outputs are denoted by A plus and B plus. Okay, so this A plus, that means next state of A will be exactly equal to the whatever you apply at the input, dA. Similarly here B plus will be exactly similar to dB. Okay, that's why you can see here dA is equal to AX plus BX, A plus is also equal to AX plus BX. Similarly dB is equal to A bar X and B plus is also equal to A bar X, because in D flip flop output is exactly similar to the input. So this is my second step, writing the flip flop output equation. So in case this was not a D flip flop, in that case we would have used the characteristic equation to find the next state of this flip flop by using the input and feeding that input in the characteristic equation of that particular flip flop which would have been given in the circuit. But right now we are provided with a D flip flop. So let's proceed further. So this is flip flop output equation, and then third step is circuit output equation. So our circuit output equation is equation for this Y. We can see that this point is, there are different points, this point, these 2 points are corresponding to, this is B and this is A and this is X and this corresponds to X bar. So this becomes A plus B into X bar. Is it clear? So this is A plus B and it is getting multiplied with X bar. So this Y, this is equivalent to A plus B into X complement. Okay, so this is the expression for Y. So we have derived these 3 steps. We had covered these 3 steps in our yesterday's lecture also. So I have repeated these 3 steps. Now I am proceeding to the 4th step, which is the most important step. These 3 are the basic steps, and if I am able to perform this 4th step correctly, then 90% of the question is taken care of. Okay, so let's prepare this state table. So I have again mentioned these 3 expressions: A plus is equal to AX plus BX, B plus is equal to A bar X, and final output Y. Output Y is equal to X bar into A plus B. Now preparing the state table. State table means present state. Okay, it will change according to the input X, and we will get the next state. Okay, and the final output, which is denoted by Y. So again, present state is denoted by A, B, and next state is denoted by A plus, B plus. Okay. So there are 3 I am repeating these X and Y. So A, B, X and A plus, B plus Y. A, B, X are the controlling variables. We have to feed the values of these A, B, X, and we will get the next state values of A plus, B plus and the final output. Okay. So there can be 8 possible cases: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay. So this is the present state and X. using these things we can write the next state. So you can do it on your own as well, but for the time being you can check. A plus, I am writing this column for A plus, okay. This A plus thing, A plus is equal to AX plus BX. That means it can also be written as A plus B into X. That means wherever X is 0, wherever X is 0, here X is 0, here X is 0, here X is 0, again here X is 0. So wherever one of the thing in the product is 0, output will definitely be 0. I have replaced 4 zeros, and again I can check wherever A plus B is 0, that would also result in a 0. So A plus B is 0, first case it is 0, second case A plus B, this thing A plus B, it is 0, and in rest of the cases A plus B is 1, okay. So this A plus B, 0 plus 1 into 1, that becomes 1. Similarly this thing also becomes 1, and last one is also 1. So I have prepared the column for A plus. Similarly I can prepare the column for B plus, okay. So let us prepare the column for B plus using this expression A bar X. Again I can see that wherever it is the product of A bar and X, that means wherever X is 0, output must be 0. So this is X is equal to 0, 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 okay. So this A bar, now we can check the value for A bar. So wherever I can see that A bar means wherever A is 1, that bar will become 0. So A bar you can check here, A is 1 and it will become 0. So A is 1, that it will result into 0, A is 1, it will become 0, A is 1, it will become 0. But for the rest of the cases A bar will become 1, 1 into X 1, here also 1. So these are the entries for B plus, okay. So proceeding further for Y, Y is X bar into A plus B. That means wherever X is equal to 1, I will be getting 0 output, because X bar, that means I am multiplying it with X bar. That means if I get X is equal to 1, then X bar will be 0, and 0 into something will be 0. So I am checking wherever I am, this X is equal to 1, so this must be 0, X is equal to 1, this must be 0, X is equal to 1, this must be 0, last case X is equal to 1, this must be 0. And now checking A plus B, wherever A plus B is 0, again Y will be 0. So this first case A plus B is 0, and for rest of the cases you can see that A plus B will be giving you value 1. So in this case 0 plus 1, 1, this 1 plus 0, 1, and this 1 plus 1, 1. Okay. So this is the calculation of next state and the next outputs. Okay. So let us proceed further and prepare the state diagram. Modified state table, this is not required because the given state table is sufficient enough. We have to prepare the reduced state table in those cases where we are provided with the state table which has been given by the examiner. So we have to prepare the reduced state table, but in this case state table is also prepared by us only. So we need not to perform that state reduction step. We can straightforward straight away go for the last step, which is mentioned here. State table is ready now, state diagram. So last step is state diagram. If anybody is having any query in this state table step, so you can send that query in chat box, and till the time I am preparing the state diagram. Okay. So changing the color. So first you can see that the states are either 0 0, 0 1, 1 0 or 1 1. So 4 states are there, 0 0, okay, 0 1, 1 0 and 1 1. So there are 4 states, and this we have already seen in the previous step in which the circuit was provided to us, that this y is dependent on x, that means it is a Mealy type circuit. Okay, and in the previous slide here, and in Mealy type circuit the output and input both are written on this arrow, the state transition arc. Okay, the transition arc. So let's proceed here. It is a Mealy circuit, that means both input and output will be written on the state transition arcs. So checking the first row, you are in 0 0 state, you get x is equal to 0, next state is 0 0, that means you are in 0 0 state, x is equal to 0, and you are in this same state only, and at this point of time output is 0, output is 0. Okay. Second row, 0 0 and you get a 1, you reach 0 1, you are in state 0 0, if you apply input 1 you will reach state 0 1, and in this output is also 0, output is 0. Going to the third row, you are having AB 0 1, that means state is 0 1, you are in this state, and if you get a 0 you will reach state 0 0, that means this thing. If you apply 0 at input you will reach 0 0, and at this point of time output is 1. Okay. Fourth row, 0 1, input is 1, you will reach 1 1, that means this transition. If you apply 1 input at this 0 1 state you will reach 1 1, and at this point of time output is 0. Okay. Then fifth row, 1 0, current state is 1 0, and if you apply a 0, that means here you are in 1 0 and you apply a 0, you will reach 0 0, and output is 1, output is 1. Next row, you are in 1 0 and you get a 1, you will be in 1 0 this state only, because 1 0 next state is also 1 0, that means the next state of this state is the same state only, that means state is not going to change. 1 0 you are applying input 1, you will be staying in this same state and output is 0. Okay. This last two rows are left now. 1 1, you are in state 1 1, applying 0 input, you are reaching 0 0, that means this thing, and output is 1, output is 1. Last row, 1 1, you apply input 1 and you are reaching 1 0, you are in 1 1, you apply input 1, you reach 1 0, and output is 0. So this is the last step, preparation of state diagram. So in this way we have converted a state table into a state diagram. So I will be waiting for some confirmations from your side in the chat box, and then I will proceed further. So till the time I am summarizing, so I am expecting some confirmation from your side that it is clear, because this is the end of this topic of analysis part. Okay, then I will proceeding to the design part. So if I get few confirmations in the chat box, then I will proceed further. So what we have covered, what we have done is we have written the input equations using the output equation, then circuit output equations, then state table, then state diagram. So these are the steps. So Jitendra has replied. So I think I can proceed further. If there is any query, you can type in the chat box. So this is analysis of clocked sequential circuit. So this question, this next question, I am leaving it as a practice question, which is a T flip flop. So the only thing I am doing one step in this, that in that this T, this is my input X, okay, and this is X, and this is, you can see here, this is B, so Bx. So TA is equal to Bx, TA is equal to Bx, okay. Similarly this TB, this is TA, and TB, this TB is equal to X, TB is equal to X. But now this is not a D flip flop. In D flip flop output is equal to input. So if this would have been a D flip flop, then next state would have been identical to this Bx and X, but this is not the case. So we have to use the characteristic equation of T flip flop. Characteristic equation of T flip flop says that the next state Qn plus 1 is equal to T XOR Qn. That means if I want to calculate the next state, A plus will be equal to TA XOR the previous version of A. Okay. That means TA is equal to Bx, so Bx XOR with A. So this is the expression for A plus. Similarly, B plus will be equal to TB XOR B. B is the previous output of this flip flop only. So TB is equal to X. So X XOR B. So these are the expressions which are going to be used for the next state computation. Okay. So if we having flip flops other than T flip flop, we have to use the characteristic equation to find the next state equation. That means in this case, again you can check here, output is A and B. So in this case output is independent of the input. So this is not a Mealy machine, it is a Moore machine. Okay, this is a Moore machine. So again the table will be same. A, B will be the present state, X will be the input, A plus and B plus will be the next state, and Y will be the output. So here you are having expression for this A plus. Using this A plus expression you can write the value for A plus, and this using B plus you can write values for B plus, and Y you can check Y is equal to A dot B. So product of these two things will appear at this Y. So in this way you can prepare the state table for this circuit, and then state table can be easily converted into state diagram. So I hope it is clear. Now we can convert any given circuit into a state table by using the characteristic equation of that particular flip flop which is being provided to us, and preparing the state table, and then finally converting that state table into a state diagram. Okay. So this is the analysis part. I hope it is very much clear now. We can prepare state diagrams for any given circuit which is having any kind of flip flop. We have to just remember the characteristic equation of that particular flip flop. Okay. So let us proceed further to the design part, designing of finite state machines. So designing, first step is from the word description and specification of the desired operation derive a state diagram. In analysis part, state diagram was the last step, but in designing process, this state diagram is the first step. Okay. And there is a question from Jitendra, sir, is there any effect on state table if it is independent of external input? State table if it is independent of external input. Input will always be dependent on that, next state will always be dependent on the input. Only thing is the output can be independent of the input, which will be categorized as Mealy machine and Moore machine. But in both Mealy or Moore, the state will always be depending on the input. Okay. So we cannot say that the state is independent of the input. State is dependent on the input, but output can be independent, depending on that it can be Mealy or Moore. Okay. So getting back to the design part, first step is you have to prepare the state diagram. Either the state diagram will be provided to you by the examiner, or you can prepare the state diagram from the given word description. Okay. Then reduce the number of states if necessary. So if state diagram is provided to you by the examiner, you need to perform this step. But if state diagram is prepared by you only, then you need not to perform this step, because while preparing the state diagram this thing would have already been taken care of, because you are preparing the state diagram from the given description. Okay. There is one more question from Yash, sir, for output also we have to use characteristic equation. No, for output we need not to use the characteristic equation. I am getting back to this circuit. You can check here, this is the final output. This final output Y is equivalent to A dot B. It is independent of the characteristic equation. by using the characteristic equation we can obtain A and B, but to obtain Y we are not going to use the characteristic equation, we have to simply use the values in the table. From here we have to simply multiply these values A into B and write the product here. Okay, I think I am clear. Yes, you can reply in the chat box till the time I am proceeding further. Okay. So getting back to the design part, first step preparing the state diagram, reducing the number of states, then assigning binary values to the states. So if there are states A, B, C, D, then I can replace A by 0, 0, B by 0, 1, C by 1, 0, D by 1, 1. Okay. Obtain the binary coded state table, then prepare the state table, then choose the type of flip-flop. We are going to prepare the circuit, so we have to be very much clear that which flip-flop we are going to use to design the circuit. And it will be very much easier if examiner has not mentioned to us, then we will be using the D flip-flop because it is the easiest one, output is equal to input. Okay. So choose the type of flip-flop, if it is not mentioned we will use D flip-flop. Okay. Then derive the simplified flip-flop input equation and output equations, draw the logic diagram. So this step might not be clear in the written form, but when we will be computing that step, when we will be performing that step, it will be clear to us. So let's start with the question. Okay. So I have deliberately taken a question in which state diagram is not given to us. Otherwise it would have been very much easier. We could have simply converted that diagram into table. From table we would have prepared the K map and expression and circuit. It would have been very much easier, but I have deliberately taken a question in which only statement is provided to me. Okay. So let's understand this statement first and try to prepare the state diagram on our own. Okay. So design a circuit that detects a sequence of 3 or more consecutive ones. That means we are going to prepare a circuit if it is detecting the inputs, and if it is detecting first one, it will not respond, second one it will not respond, but as soon as 3 consecutive ones are detected, that means 3 consecutive ones are being fed to the input, the circuit will recognize, okay, something has happened, the desired operation has happened. It was detecting 3 ones, and as soon as 3 ones are detected, only then output will be high. Till the time 3 ones are not there, output will be low. Okay. So this is the given description. That means I am going to design a circuit which detects 3 or more ones. That means after 3, if I am getting 4th one, output will be high, 5th one, output will be high, minimum 3 1 have to be there. Okay. So let's prepare this like something like this, that let's suppose this initially, let's suppose input is 0. Okay. I denote it as state S0. Input is 1, then it is denoted as S1. That means first one, ये पहला 1 detect होगा, तो I am denoting it as state 1, but output will be 0. यहाँ पे भी in the first step output is 0. Output will be 1 only when we are getting the 3 consecutive 1 at the input side. Okay. So if second one appears, second one, that means another input is 1, that means 2 ones have appeared, then I will reach one step further, S2, but output will still be 0. Okay. Third one, if I receive another 1, that means input is equal to 1, that means 3 consecutive ones are there. This is the first one, this is the second one, this is the third one. So this is my desired state, S3. Okay. Now output will be 1. Before that output was 0. And if there is a 4th one or 5th one and so on, I am going to remain in S3 only. Okay. Because I am provided with a question, minimum 3 or more, that means if there is 3 or 4 or 5 or 6 or any number higher than 3, it will be it is same to me. Okay, so I am going to remain in S3 and output will be 1, output will be 1. Okay, so this is the basic. So let's convert this into a state diagram. Okay, so state diagram. So I am in state S0. Can somebody reply in the chat box whether this description is going to result in a Mealy machine or Moore machine? Whether I am going to design, whether the final design will be a Mealy machine or a Moore machine. Okay, you can simply see that S0 output is 0, S1 output is 0, S2 output is 0, S3 output is 1. Okay, that means it is going to be a Moore machine. Okay, I am in state S0. If I get a 0, then I will stay in this state only. If I receive a 0 at the input side, if I receive a input at the 0 side, then I will stay in this state and wait till the first one appears. Okay, so if I receive 3 zeros, 4 zeros, 5 zeros, I will stay in the S0 and wait for the first one so that the process starts. Okay, if I receive a 1, then I will reach state S1, but output will still be 0. Okay, now if I am in S1, I am in state S1, I am in state S1. If I receive a 0, that means sequence has broken, sequence has broke. We are expecting the sequence 1 1 1, but after receiving first one I get a 0, that means I have to restart. Okay, that means if in S1 I get a 0, I have to go back and wait for the fresh one sequence. Okay, but if I get another one, that means second one, for this second one I will be in S2, that means I will reach S2, output will still be 0, output will still be 0 in S2 if I receive a input 1. Okay, now I am in S2, I am in S2 and I receive a 0. 2 ones have appeared, now third bit is 0. Okay, if third bit is 0, then I have to restart. Okay, but in case I get a third one, if that third one is also there, then I will reach state S3 and this time output will be 1, because this is a desired state. I was expecting 3 consecutive ones, so 3 consecutive ones have appeared, first consecutive, second consecutive, third consecutive, and in between if there would be a single 0, ek bhi 0 aayegi, then you will be reaching back to the first state S0. Okay, so you have reached state S3. Now if in S3 you get a 0 input, you will again go back to S0, but if there is input 1, that means fourth one is there, fourth one, fifth one, sixth one, any number of ones are appearing after the 3 ones, you are going to stay in the state 3 only. Okay, so this is a state diagram. So this state diagram will be most probably provided by the examiner only, but I have deliberately taken that question. We have prepared the state diagram first on our own, and now we can prepare the state table. So first of all we can assign the binary states. Let's say S0 is equal to 0 0, S1 is equal to 0 1, S2 is equal to 1 0 and S3 is equal to 1 1. Okay, so I can replace these states by these things and then I can prepare the state table. So you can check there, this is the same thing, the same which I have prepared. I am in state S0, if I receive 0 I will stay here only, I will be in state S0 only. If I receive first one I will reach S1, okay, second one S2, third one S3 and fourth one in this S3 only. And whenever I am getting a 0 at the input, you can check I am going back to this first state of S0 only. So, this is the same state diagram. I am using S0 is equal to 0, S1 is equal to 0 1, S2 is equal to 1 0, S3 is equal to 1 1. Okay. So, let us prepare the state table now. Present state A, B, input X, next state A plus, B plus and output Y. Okay. So, A, B and X 0 0 0 first column you can see 0 0 0 0 0 1, this is the normal input side 0 0 0 till 1 1 1, this is 0 0 0, this is 1 1 1, all possible cases are being mentioned at the input side. Now, from the diagram we can see that 0 0's next state is 0 1, 0 0 if you apply a 0 at the input side, it will remain in this state only. You can have checked that whenever you are getting input 0, you are going to S0, S0 is 0 0. So, whenever X is equal to 0, next state will be 0 0. So, for these 4 cases you can see that next state is 0 0 0 0 0 0. Okay. And whenever I am getting 1, whenever I am getting 1, I am proceeding further 0 0, next state becomes 0 1, 0 1 1, next state is 1 0, 1 0 1, next state is 1 1, 1 1, that means this S3 is there, that means 3 ones have already appeared, and after that 4th one, 5th one, 6th one, more number of ones are there, then I am going to stay in this S3 only, we have discussed. That means next state of this 1 1 will be 1 1 only, we are not going to proceed further. S3 will be, next state of S3 will be S3 if I receive 1. Okay. So, this is the transition, and similarly output you can see this is equivalent to S0 0 0, this is S1, this is S2, this is S3. So, in S0 output is 0, in S1 output is 0, in S2 output is 0, only in S3 I am getting output as 1. Okay. So, in this way we have prepared the output section from this table only. You can see here only S3, here or you can see from here only S3 is giving you high output, and S0 output is 0, S1 output is 0, S2 output is 0. So, that is being depicted here, S0 to S2 output is 0 and S3 output is 1. Okay. So, this is the state table. Now, from the state table you have to note down the minterms. For A plus, writing the minterms, I am highlighting these minterms, A plus 1 1 1. So, these 3 ones correspond to 0 1 1 3, 1 0 1 5, 1 1 1 7. So, 3 5 and 7. Similarly, for B plus 1 1 and 1, which corresponds to 0 0 1, that means 1, this one corresponds to 5 and last one is 7. So, minterms for B plus are 1 5 and 7. Similarly, minterms for Y, these are the 2 ones which correspond to 1 1 0 and 1 1 1, that means minterms for Y are 6 and 7. Okay. So, after preparing the table we have noted the minterms, and once these minterms are ready we have to solve 3 K maps, one for A plus, one for B plus, one for Y. So, in the next step we can see that this is the K map 0 1 3 2 4 5 7 6. So, 3 5 7. So, I am getting the expression dA is equal to A x plus B x. Okay. Similarly, for here dB it is Ax for dB expression is Ax plus B bar x. Similarly, for this y, I am getting the expression A dot B. Okay. So in neat and clean form, if we see that these are the three minterm sets, if I solve 3 K maps, I am getting 3 expressions. So again, I have mentioned these 3 expressions here. A is equal to dA is equal to Ax plus Bx, dB is equal to Ax plus B bar x, and y is equal to A dot B. And as you can see, I have used D, that means I am going to design this using a D flip flop. Okay, so using a D flip flop, 2 D flip flops are there. DA, QA, QB. This QA will be A, this is not QB, this is QA bar. QA complement acting as A bar. This is the clock, this is the input. Another D flip flop, DB, clock, QB acting as B, QB bar acting as B bar. As it is a synchronous circuit, so the clock must be common, preparing the clock connection. Okay, so this is the synchronous mode connection. DA is equal to AX plus BX, that means AX Bx. DA is equal to Ax plus Bx. Similarly, DB is equal to Ax plus B bar x. Ax and B bar x. Okay, and for y we need to prepare AB. So I can take this A from here and B from here, and this can be my y. This is flip flop A, this is flip flop B. So this is the design of this sequence detector. Now that means this circuit can detect a sequence of 3 consecutive ones. Okay. Similarly, examiner can give you a question in which the sequence might be changed. Instead of 1 1 1, he will give you 1 1 0 or 1 0 1. So we have to practice for those questions as well, in which the sequence might be different, but 99% of the cases examiner might give you a state diagram directly. Okay, but we must be prepared. If we are provided with a description, we can convert that description into state diagram into state table. From the state table we can note down the minterms, from the minterms we can solve the K maps, from the K maps we can obtain the expressions, and from the expressions we can design the final circuit. Okay. So I think it is clear. So with this we come to the end of this designing part as well. Okay. So thank you very much. So if there is any query, I am waiting for few seconds. If there is query from your side, then you can type in the chat box, and if it is clear you can give a confirmation, and then we will close the session. So if there is any query, I am just waiting for few seconds in the chat box for your replies. If it is okay, then we can close the session.